Welcome back to our course Measure Theory for Probabilists. Now we're in the chapter of integrals, and we want to compute integrals of functions which will be measurable functions. And since we will need approximation theorems for these integrals, we today first have to see how measurable functions can be approximated. So let's get started. Approximation of measurable functions. We already know something what is on this slide here. We had in one of the previous videos that if you have a function and you have a sigma field here on omega prime on the codomain, then we define sigma of f. So you look at f to the minus 1 of a prime, so the pre-image of a prime for all a prime and f prime. Then this here is in fact a sigma field, and we will need that often here in this video today. And what we also had is the image measure. And we also had that the image measure is in fact a measure, unsurprisingly. So what was the image measure? F asterisk mu of a prime. That's here mu of the set f is in a prime. Well, and today the first main thing we need to see is the following. So we had the sigma of f here. And that's a different way of constructing this. So we have here a generator of f prime. So c prime generates f prime in the sense that sigma of c prime is f prime. Then, okay, what's this here? Or what's this here? So that's f to the minus 1 of f prime. Because sigma of c prime is f prime, and f to the minus 1 of f prime. Well, that's essentially this here. So that's sigma of f. So this here is sigma of f. And on the left-hand side is something different. Here I pull back only the elements of c prime, and afterwards I generate the sigma algebra. So I'm exchanging sigma and f to the minus 1 here. And the result is the same. This lemma here claims. Let's try to prove this. First of all, we know that this here is in fact a sigma algebra because that's sigma of f. And I can write the following. Sigma of f to the minus 1 of c prime, so the left-hand side, that's a subset of, well, f to the minus 1 of sigma of c prime. So why is that? So I use more sets here than just those in c prime. So I get a larger set. Okay, this is a sigma algebra, so that's the same as f to the minus 1 of sigma of c prime. And this is already the first direction here, so subset. The other direction, I need to define something. F prime tilde, I will call this, which will be in general a subset of my f prime, which is sigma of c prime. So what I do here, I take all a prime in f prime with a property, and the property is that f to the minus 1 of a is in sigma of f to the minus 1 of c prime. Yeah, sigma, so that's this object here. So what do we want to see? We want to see that every set in sigma of f is also in here. And those in sigma of f are just the sets which are written here. And I need to see that all of these are element of this here. And once I have this, so to show is that f tilde prime equals f prime. And then all members in f prime have the property that this here holds, which means that, okay, sigma of f subset or equal then sigma of f to the minus 1 of c prime. Which means, well, this here is a subset of this here, and sigma of f is this here. Okay, then I have it. So I need to show that f tilde prime equals f prime. Then I'm done. Yeah, so first of all, I can show, but I don't want to do this here, that f prime is in fact a sigma algebra. You do this by showing that, well, this property here is stable under intersections and so on. And once I know this, then I know, for example, c prime is subset of f prime tilde. Why is that? Well, every set a prime in c prime so has the property that f to the minus 1 of a is in f to the minus 1 of c prime. So it's also in sigma of f to the minus 1 of c prime. So that's clear. And f prime is also subset of f prime. Okay. And for this reason, the sigma algebra generated from this here is subset of the sigma algebra of this here, subset of the sigma algebra of this here. But the sigma algebra generated by c prime equals f prime. So I know this here, f prime is sigma of f tilde prime, but f tilde prime is also sigma algebra, so that's f tilde prime. And I'm done. Okay, so we now know we can exchange sigma algebra generated by the function and the function itself. Let's define several things. Maybe we had this already, maybe we didn't call it like this. So I need two measurable spaces, omega and omega prime. And a function is f prime measurable if, well, if the pre-image of f prime is a subset of f. So in fact, that's similar to continuity and topologies. So you might remember f is continuous if f to the minus 1 of, well, let's call it O prime, that's a topology on omega prime, is a subset of O, which is in this case here, that's the topology on omega, and this here is the topology on omega prime. So this here is really similar. The only difference is here I have topologies and here I have sigma algebras. Then just to define this here, for a probability space and a measurable function, then I call the measurable function x a random variable with values in omega prime. The image measure, which we had before, is called the distribution of x. We will need that in the next videos. Then if omega prime is the real numbers, or, well, including infinity or something, we say that f is Borel measurable, because here is the Borel sigma field. So measurability in this case is also called Borel measurability. Then we need special function, because recall we are in the section approximation of measurable functions, and we are going to approximate these by so-called simple functions. And simple functions are functions like this here. F is a sum. Over here are indicators of some measurable sets. And ck are just some prefactors. Such functions are called simple. For example, indicator functions themselves are simple. Okay, some examples. First is very simple. The identity function is measurable because, yeah, well, this here holds, and that's pretty clear. Then continuous functions are measurable. I already told you that the concepts of continuity and measurability are pretty similar. However, how do we prove this? So continuity means this here. And we had the lemma here, which says I can exchange the sigma and the f to the minus 1. And for this reason, I can write the following. F to the minus 1 of, well, I have here the Borel sigma algebra of omega prime, f to the minus 1 of this here. Okay, that is, so Borel sigma algebra is sigma of omega, that's by definition sigma of O prime. I can exchange f to the minus 1 and sigma. F to the minus 1 of O prime is a subset of O because f is continuous. That's the definition. And sigma of O is the Borel sigma algebra of omega. So I have shown that, well, the defining property of measurability holds, so continuous functions are measurable. Nice. Then functions which have codomain 0, 1 are measurable if and only if the pre-image of the 1 is in the sigma field f. And in this case, sigma of f can be written down explicitly because when you have a set here, there are just 4 subsets of this here. Okay, empty set, the image is the empty set. The pre-image of 1, this is this here. And measurability then, gives you that f to the minus 1 of 1 has to be also in f here. In order to be a sigma algebra, I also need the complement and the full set here. Yeah, so this here always holds, and measurability only holds if this here is the case. In the manuscript, you also find examples of sets or functions which are not measurable. And I'm not going to explain this here. It's a construction by Vitali, and it needs the axiom of choice. Two examples for probability theory. So we already had that x star p, so that's the distribution of x under p. Y star q is the distribution of y under q. So q is also a probability measure. If they're the same, we say that x and q are identically distributed, and we write x tilde y. It's important to see that p and q, they don't have to be the same. So you have two probability spaces, and x and y, they have to take the values in the same space. That's clear. And on this space, you can have a distribution, which is, so a measure, which is the distribution of x, which equals the distribution of y. And they're identical if these two are the same. Another thing is joint distributions. if you have a family of random variables, they can also have an image measure. So that's a high-dimensional measure. The dimensions you have is all elements in I here. And the distribution of this here is called the joint distribution of this family here. We will also need that in probability theory. Then some more lemmas, and which eventually lead to the approximation result that we want. First, f C prime is a generator of f prime. And they claim that a function is measurable with respect to f prime if and only if, well, if f to the minus 1, if here would be an f prime, that would just be the definition. But I have a C prime here, which means I need to check this property for fewer sets, only those in C prime here. Let's just see if we can prove this. So what I need is that f to the minus 1 of f prime is a subset of f. But here I can now make use of the lemma 3.2 f to the minus 1 of sigma of C prime. I can exchange the f to the minus 1 and the sigma, as we saw. Oops. That's sigma of f to the minus 1 of C prime. That's a subset of, that's a subset of sigma of f y. First of all, I have an if and only if here. Okay, one direction is clear anyway. If it's measurable, then this here must be the case. And we're just showing that if this here is the case, then the function is measurable. So this here is the case. So this here is a subset of f. So that's the reason for this subset. And what is sigma of f? Well, f has a sigma algebra anyway. So this here equals f, like this. Okay, now I have shown that f to the minus 1 of f prime is a subset of f, which is what I wanted to have. Okay, that was one, and all the others are pretty clear anyway. I'm not going to show them. So if f is measurable and g is measurable, then the composition is also measurable. And you prove this by saying, well, the defining property is anyway f to the minus 1 of f prime is a subset of f. And doing two steps here just gives you measurability of the composition. Another thing which also uses here the first one which we had, a real valued function is measurable if and only if, well, these functions here, so these sets here are measurable. And the reason is that the sets, well, so the set system minus infinity to x in Q generates the sigma algebra, so the border sigma algebra on R. So what is written here plays the same role as the C prime above here. And in the first property here, we saw that we need to check the property f to the minus 1 of C prime only here on the generator. And this is essentially here what happens. Then a simple function, okay, I need some restrictions. So the CKs must be pairwise different in order to make sense. Otherwise, I could combine these two anyway. Is measurable, so the simple function is measurable if and only if all these indicators here are measurable. Okay, that's also maybe not too surprising. And with this, we can now also show that if you have measurable functions, linear combinations are measurable, quotients, products are measurable, and also suprema are measurable. In particular, also the absolute value of f, for example, is also measurable because it's the maximum of f and minus f. So how do you prove, for example, that the sup of fn's, or a countable number of fn's, is measurable? When you have this, well, the inf works the same, and lim sup and lim inf are anyway only sups of infs. So we have to prove one, and then we have all four assertions. So what would we have to prove? Here we saw that we would have to prove this here. So that's the the pre-image of minus infinity to x, which means here I consider the set of omega with the property sup over all n, fn of omega is smaller or equal to x. So, and when I see that all these here are in f, then I'm done, because then I can read from here that means measurability. Okay, but if a sup is smaller or equal to x, what does that mean? That means that all of these here have to be smaller or equal to x. Sup n f, sorry, not sup. I wanted to say fn of x. No. Ff on omega is more equal to x. So now it works. So the sup is more equal to x if and only if all of them are small equal to x. So I have this here, and apparently, well, these here are measurable because fn is measurable, and the finite, the countable intersection of measurable sets is also measurable. So I'm done. So I'm done with the whole thing. Sorry, so that was the proof here of the second part. The proof of the first part I almost forgot, but that's essentially, so that's second part. First part, I need here that the composition of two measurable functions is measurable, because then I can say I have a function psi of omega. That's the composition of f of omega and g of omega. This here is measurable. Why is it measurable? Because f and g are measurable. So this is measurable. And then I can write, well, x and y as a tuple maps to ax plus gy, for example. That's continuous. So this function here is continuous, which means it's measurable. So I have the function first, omega goes to psi of omega, and psi of omega goes to this here. So I can write this function here, af plus bg, as a composition of two measurable functions, the psi here and the other function here. And compositions of measurable functions, they're measurable, so we are done. And it's similar for the product, and it's similar for the quotient. And finally, we come to the approximation result that we want to have, which is now really simple. Every measurable function can be approximated by simple functions in such that the limit is increasing. And the proof is just by writing down what the approximation looks like. Fn of omega is n minimum 2 to the minus n, 2 to the n, f of omega. We claim first of all that this here increases to f. Well, if n is bigger, then this here won't play a role anymore. And if n is going bigger, well, here what does it do? It rounds f of omega to the first n digits in a binary representation of the number. And then it becomes finer and finer. Of course, this here, because the square bracket is always small or equal to f of omega, means that I approximate from below my f of omega. And increasing n makes the resolution arbitrarily good, which means that fn of omega here increases to f of omega by construction. And yeah, these are simple functions here. They are simple because if f of omega, this here can only take values, so the whole function can only take values which are multiples of 2 to the minus n. So that will be a simple function. And when it's a simple function measurable, well, we know this if the pre-image of any set with constant value is measurable. And this here means, for example, this here needs to be measurable. So, yeah. When is this, for example, smaller or equal to x? Well, I can just say it's smaller or equal to x if and only if, something with f of omega is smaller or equal to, well, something times x, or some rounding operation I still need. But since f is measurable, this set will anyway be measurable, which means that this is measurable. And fn of omega is a simple measurable function increasing to f, and I'm done. Okay, very good. And we're also done with today's video. Next time we will be introducing the integral. See you then.